Hello, my name is Miko Stulajter. I'm a second year PhD in the Joint Doctoral Program, and today I'll be presenting on lower dimensional network representation of chemical space. So a network can discretely represent chemical space. Representing chemical space as a set of discrete points allows us to obtain information on reactions such as reaction pathways, activation energies, or total energies. Current approaches for exploring chemical space rely on sets of rules derived from knowledge that we have in chemistry, but the networks that we plan on building here are built through a set of rules describing what bonds can form or break and kind of enumerating through all the combinations. So we don't really rely on chemistry knowledge. The networks that we build can be unbiased and enable us to efficiently explore and search chemical space. Within each of our networks, the nodes are molecules and the edges are individual bonds either breaking or forming. Within each network, each node has the same stoichiometry, which means the same number of atoms. And here on the slide, we give two examples of networks. The first is for a formaldehyde network, which doesn't have a lot of node options. And the second is for two formaldehydes and two waters, and we can see that this network is much, much larger. So the rules for building these networks are based on the smarts representation, which is a way for describing bond breaking and forming for us. We specifically look at networks built from carbon, nitrogen, oxygen, hydrogen atoms. We could look at different atoms and different rules, but we kind of stick to these atoms for now. We only explore a small subset of all the allowed rules to kind of keep our network sizes manageable. And here we list all 40 of the rules that we utilize, which are mostly single, double, and triple bonds. So our networks kind of scale superlinearly. So the systems that we look at contain either 1 to 3 hydrogen cyanides or 1 to 4 formaldehydes, and anywhere from 0 to 5 waters. And we can see the number of nodes and edges for these networks scale superlinearly. And we can see when we add water to the hydrogen cyanide networks, this leads to many more possible nodes and edges compared to the formaldehyde networks, which causes the networks to grow much more rapidly. We can also do a little analysis on our networks. So the first thing that we can look at is the average path length, which tells us how many steps on average it takes to go from one node to another, or in our case, what we're interested in, one molecule to another. And we can see as the network grows, the number of steps it takes also grows. Another thing that we can look at is the fractal dimension, which gives us a sense of the dimensionality of the network or how complex it is. And we kind of calculate this three different ways. The first way is the compact box burning method. The second is the maximum explosive mass burning method. And the third is the greedy coloring method. And we can see on the graph that all of these three methods give roughly the same values. And for all the networks that we explore here, they're all less than three-dimensional. So they're much lower dimensional compared to 3n minus 6, which is what normal chemistry space is considered. Another measure that we can look at is density, which measures how many of all possible edges are present in our network. And we can see as the number of atoms is increased, our networks become more and more sparse. In conclusion, the fractal dimension of the individual network stoichiometries show that the networks are a lower dimensional representation of the underlying reactive potential energy surface. As I mentioned, the reactive potential energy surface is 3n minus 6 dimensional, where n is the number of atoms, and we can see our networks are on the order of 3-dimensional, which is a much lower dimensional representation. The preliminary findings of our study suggest that a discrete representation of chemical space can be advantageous as it can be searched more efficiently than actually looking at the potential energy surface. Some future directions are looking at the impact of individual rules and kind of seeing how they impact the growth of our networks. Another direction is looking at an informed method for generating larger networks, because right now it is computationally prohibitive to really build out very, very large networks because the number of nodes and edges scales very fast. So kind of having a way to bias which nodes are generated and expanded would be very beneficial. Thank you for listening, and that's my presentation.